All right, our next speaker is Ryoh Fuji-Hara, who is a professor of mathematics at the Graduate School of Systems and Information Engineering at the University of Tsukuba, Japan. So without further ado, let's welcome Ryoh.
Thank you. Charlie and I are friends a long time, since maybe 1980, around 1980. So I'm glad he joined our senior student group. I'm earlier than retired. Thank you very much. And I worked 1 day a week for the patent office, and there I have some deep learning programs. So I explained I have to learn how very much in the deep learning recently. So in the depth, in the process, I found some combinatorial programs. So I like to explain that. So deep learning is a kind of directed graphs in the which one? This way? Which one is right? Oh, this is right. Okay, thanks. This is the directed graphs. The second one. Those parts, two parts, that's bipartite, complete bipartite graph, like that. And the complete bipartite graphs are connected like a chain. Okay, and flow is come from the input layer to the output layer. It's no reverse side. So always flow the left to right. And input is also input is always some real numbers like that. And we can get finally output here. And the data is transformed by the linear transformation like that, multiplied by matrix. Matrix is the weight of the edges, arrows edges. And x is this vector is the input data, and multiply the matrix of the weight. And then we can get this middle data. So we just pointed to some many layers. Okay. And here's the teacher data, is the correct data. We compare the two data. And we have some set of data, input data and teacher data. And about 100 of that. Each 100 data, we compute this, we call it error function. And this is almost same module of the regression. Okay, regression. Think about the regression, so it's easy to learn. But it's too many parameters. We can compute like a regression. Okay. We estimate W weights step by step. So it's computed. We don't discuss our computation method. So, error is a kind of evaluation data. We have many data, 40,000 batches. Each batch has about 100 pair data. And the error is going to the row step by step. And if we the two dimension, we saw this kind of step. One, we have a problem in this process called overfitting problem. Because many parameters, we have a similar problem like a regression. In the regression, if we have many parameters, we have this kind of overfitting problem, same overfitting problem. And testing error is we prepare some set of data which is not used in learning. So we test sometime, and then this is a normal case. This is not overfitting. It's not happen. Usually, very usually, we have testing overfitting problem because we have many parameters. So, this is quite usual things, not rare. Okay. In the deep learning area, people doing this kind of things. This is most popular things to prevent the overfitting. We selected up with some percentages. We selected some nodes in each layers, and the rest of the edges is not we don't use the system. We use only partial nodes, okay. And each time of the mini batches, we change this kind of set. Okay. This kind of I just tested that exam that we selected randomly. That each node is almost uniform distribution, but edges not uniform, quite uniform. So more variance, more bigger variance. So nodes are usually quite even, but the edge is not even. In this kind of thing. This is a 100 first average 100 nodes and 70 nodes, and we dropped 30%. Then you have this kind of distribution of the frequencies. Most used edges is 545 within 1,000, and the lower was 430 frequencies. So quite big variances. So this kind of things happen in the there's an example in the design experience. Two-factor design, two-factorial design. Suppose we have two factors, okay, factor A and then factor C, and factor A have 3 levels, factor C have 4 levels. We have to examine each combinations and the data, and data is we need a couple of data, not only one. Now, suppose we have 3 assistants, okay, in the lab. They can work together in the same time, simultaneously. Then we broke down the small design, and the 3 small designs, and the first assistant has this kind of small 2-factor design, and the second assistant does kinds, so on. Then we can save experimental times, right? So this kind of things we can use out before that. They use this kind of block design in the statistics. Suppose point set 2, V1, V2, and we make a block set, and each block have 2 sub-blocks. V1 is come from V2, V1, V2 is come from V2. When I talk to split block design, block size is not constant, not necessarily constant. But pictures here. So there are 2 sets. Take out some blocks and the blocks is kind of like that. For every pair x1 and x and y, so they are constant blocks which contain that. This is called split block design, type 1-1. 1-1 means one point from V1, the 1 point from V2 means that. This is same problem as the edge decomposition complete bipartite graph. Okay? It's exactly same problem. And this is example here. The 3 points from the V1, 3 points from V2, this kind of things. Every pair appears exactly one time. There are two types of the one here. Here, there are subblocks, the same 3 subblocks. Each subblock appears 3 times. Here, not every subblock is different. Okay. The both satisfied conditions. Okay. We'll discuss about that one later. Here, I found this kind of papers. They doing the almost same things, same problems, almost same problem. But their work is completely independent. They don't differ each other, completely independent. So this guy, I know him, and he published in the Hiroshima Mathematical Journal. It's quite not circulated enough. It's 1981. But this is almost the subset of the subset. This is the bipartite, a complete multipartite graph. This is special case of that. This paper was very, very for long times not referred in any people because the this is not circulated. Recently, Charlie's 3 friends put the light on this ancient paper. Vera Duke, Esther Ranke, and Alan Ging here. Alan is somewhere. And very recently, 2 years ago, only 2 years ago. So it's ridiculous. So many people are working on same things. Now, I like to define the drop-out design of type here. It's a more general of the two part like this. Okay. Point set is n subset, and distinct point sets. Okay. And the block is the n. For each CI is found from VI, subset of VI. The block size will be certain constants. And the condition here for later. Collection of any consecutive T subblocks here of the forms a split block design with a concurrence number VI. So I'll show you the picture. It's the type 1-1. It's a concept two subblocks satisfies split block design. Okay. And consecutive 1 here. The block is wrong, but the condition is only two part types here. And so if it's a type is 1-1-1, so concept the 3 subblocks here, satisfy the condition. Okay, split block design. Oh, before that, split block, I generalize split block design to the T size. Okay. So it's a in the definition, there's a VI size of VI and block size is sub-block size is a variable. So it's too many parameters. So you consider the regular dropout design. Regular block design is the block size, block is, point size is constant. Each VI is constant. And sub-block is all size K. Then automatically lambda is all constant. So we call that regular block design of type. Type is not necessarily constant. Okay. So it's automatically this kind of relation we have. One more is that if we cater the regular block dropout design is type is this one is also type this one is cyclically saturated. Okay. dt t1 the dt minus 1. Then there is a regular block plus of this one. For all t n t equal greater than n. N equal greater than t. So infinite remain one minus layers from layers. So it's quite convenient. This is one. Originally, if we have this kind of regular block design, copy this one sub-blocks to the sub-packet. So we can get that. So next one is copy this sub-block to the fourth. So infinitely you can make packet block design. This is complement. It's also trivially always dropout design. So no question about that. So one construction, one idea is from the orthogonal array or transversal design. This is suppose this is a transversal design. So groups, many groups here. So first three groups to be one block point V1. So last two groups to be V2, V2. So transverse here. So 3 points are in the V1 and the 2 points are in the V2. So we have a block. We need some statistical ground for the dropout design. Why is it good? So we have a question there. Let's consider that. This is a linear transformation that we explained before. Just think about the one node, this one. There are too many parameters. So if we consider only one node, this one, okay? So if we consider the one node, we only need this first rows. We don't need second other rows. Then, suppose we have a mini batch contain only one data. So then, each time we have one data set, okay? And the first two data, we have dropped those two nodes are dropped, so only we have two nodes are remain. Then, first data is here. And then second data, we have this kind of things, 2 and 3. Then we have this kind of then we have a kind of almost similar model of the linear regression. It's data is not complete, it's sparse data regression. Okay. And this is those parameters here only 4. So we have to estimate those 4 parameters. Then we have if we use the dropout design type 1, so x is consider x is 0, 1 meters. Okay, x is the one design area block size. If we use type 2-1 or 2-2 dropout design, the x is R lambda design. It's the block size variable. R represent R and Loveless constant. So it's kind of similar to pairwise balance design, but R is necessary to be constant. Then we have a well-known statistical result. If the sparse data matrix is X is U-wise balance design, U is one to the from D1, D is this number is 2 here. Now it's 2. Then the estimates are optimal in the sense of the statistics. This is a long story. We need a couple more hours to explain this optimality. So I skipped this optimality. Anyhow, it's a long things in the statistics. Okay. And we have time. 5 minutes more. Okay. But one more problem. It's a convolutional type of the deep learning. We call convolutional neural networks. In the models, we need a filtering. Suppose this is a image, picture of image. So we have a small number of matrix. We filter. Filter is take this kind of inner products, matrix in the product to the output is here. Then, usually, if we use all data to filter, we have too many parameters, so same happening in that overriding. So we drop some filters. So filters to be only these small numbers. Just think about 0 or 1 matrix here. We have in some mathematical notation here, we have a B matrix, size B by B, 0 matrix. And each row and each column, we have K1s. Okay. And add all of the matrix, every cell appears, in every cell, 1 appears 7 times. And every 2 rows, 1 appears 7 times. And every 2 rows, 2 columns, every 2 columns, 1 appears the same times. So this is like this kind of things. If we use cyclically, we would like to construct cyclically. It's very similar to the difference family. This 1 and 3 is a condition of the difference family. And this 2 is not in the difference family. So we are like to add this condition to the difference family. So then we can get the cyclical filter, balanced filter. I don't name the next family. It's kind of cyclic balanced filter, something like that. But this gets a much easier problem than that. Drop design. Okay, thank you.
Any question for Ryoh? Okay, if not, let's thank Ryoh again. That's all.